We will now continue with our discussion of sound and sound waves by talking about the pitch of a sound. What is the meaning of pitch of a sound? I'm sure some of you at least must have heard the word pitch, high pitch, low pitch. The quality of a sound wave which determines how high or how low the sound is, called the pitch of the sound. Now, I'm going to vibrate a tuning fork and listen to this sound. Alright, that is one sound. And listen to the next sound. Now, which of these sounds is of high pitch? You heard two sounds. Shall I repeat that? Alright, the first one. That's the first one. Now the second one. Now look at the second one. It's a very high-pitched sound. A high-pitched sound is very shrill. A low-pitched sound is flat. You see, it's a low frequency. So obviously pitch is related to frequency. There are some people who say that pitch is the same as frequency. But no, the physical property that determines the pitch is the frequency. But pitch is the sensation of sound you actually hear. Pitch is primarily determined by the frequency of vibration of the sound, but pitch is not the same as the frequency. While frequency is the physical quantity that determines the pitch, the sensation in a listener is what defines the pitch. What you hear. Alright, the sensation created high sound or low sound. So you must distinguish the two very well. Pitch is determined by frequency, but pitch is not the same as frequency. Well, I'm going to use this now to explain a concept in sound which is very interesting and has got very wide applications. Now, pitch is what a listener hears. If you don't hear a sound, then you have no meaning for pitch. Now, we're going to apply the concept of pitch in describing what is called the Doppler effect. This is again a common term. I'm sure many of you must have heard about this Doppler effect. Now, in astronomy, we have something called a Doppler shift, which is used to measure how fast a star is moving away from us. Redshift is Doppler shift. Alright, what is this Doppler effect? If a source of sound moves towards the listener, then the pitch of the sound heard by the listener is different from the pitch if the source is stationary. Have you ever experienced when a car blows its horn and drives towards you? Have you ever observed that or had the opportunity to hear the frequency or how the sound of a horn actually feels when the car blares its horn and comes towards you, or it goes away from you? You see, as the car comes towards you, the sound will become more shrill. Well, I made a very poor attempt there, and it goes away. So, as the source of a sound approaches a listener, the pitch appears to be increasing or rising. And as the source moves away from you, the pitch appears to be falling. Now, let me see if I can demonstrate that. I have a source of sound here. Listen to the sound. All right, see if you can distinguish what you hear now. Now, can you tell me what it is? Can you hear the pitch vary? How did it vary? Did it increase or decrease? Listen to that one more time. Well, actually the pitch was increasing. And that is similar to the horn you will hear if a car is approaching you. And try and listen to this and see if that makes a difference. Well, it's rather very difficult to hear it, I suppose. Now, what does that mean? Now, this is what happens when a car moves away. The frequency falls off. So what does Doppler effect deal with? Doppler effect deals with the apparent change in frequency as a listener hears when a source of sound is either moving towards the listener or moving away from the listener. In both these cases, the apparent frequency as the listener hears it will be different from the frequency if the source was stationary. If the source is moving towards the listener, the apparent frequency will be high. If the source is moving away from the listener, the apparent frequency will be low. Let's talk more about it. This means that the apparent frequency of the sound reaching the listener is different from the actual frequency of the sound if there is relative motion between the source and the listener. And this is what Doppler effect is. This apparent change in frequency of a sound due to relative motion between the source and the listener is called Doppler effect. All right, let's now look at this in a more broad way. Now, here is a source of sound, and these circles really represent waves. Now, look at this. This source is moving to the right, and look at the waves on the left and the waves on the right. Tell me, what is the difference there? I'm sure the difference is very clear. What is the difference? The waves on the right seem to be compressed, is that right? And the waves on the left is stretched out. The wavelength is greater on the left and the wavelength is shorter on the right. That means the object or the source is moving to the right. Now, why is the wavelength shorter on the right? That means the direction in which it's moving. You see, as the source is moving towards the listener, what happens is the number of waves produced by the source, the number of waves between the source and the listener gets compressed because the source is moving towards the listener. And that is what is happening here. That means each wave, as it reaches the listener, will be a little shorter than if the source was stationary. On the other hand, if the listener is on the left side, the waves are pulled away from the listener. That means each wave, as the listener receives it, will be a little longer than the actual wave. Did you understand why? Okay. The wave source is moving to the right. Now look at the separation between the waves in front of the source and behind it. This is the front because it is moving to the right. This is behind the source. Now, what difference you notice? We talked about it, isn't it? What does the separation between the two waves represent? The separation between two waves represents the wavelength. So, In front of the source, the waves are squeezed in. The wavelength becomes shorter. Behind the waves, behind the source, the waves are stretched. The wavelength is more. The apparent wavelength. The wave separation is the distance between consecutive crests, and the distance between consecutive crests is a measure of the wavelength. Alright. Now here I have another diagram. Now, suppose this is the listener and here is a stationary source. Alright. Now, as the stationary source, the wavelength on the left and on the right remains the same. So, if a listener is standing here, there will be a certain number of waves reaching the listener per second. You see, the number of waves reaching the listener per second is the frequency as he hears it. Is that right? Because the number of waves per second is the frequency. Now here we have an ambulance blaring its siren and moving to the right. Now here is another listener. So there are two listeners. There is one listener to the right of the ambulance. There is another listener to the left of the ambulance. And if you notice here, the waves in front of the ambulance, between the ambulance and this listener, are squeezed. Why? Because the ambulance is moving. While it is producing these waves, it is moving towards the listener. These waves get squeezed. That means the waves that are received by this listener are these short waves. Whereas this listener, the waves are stretched. The waves are pulled away from him because the ambulance is moving away. It produces the sound and moves away. The waves get stretched. So the wavelength of the wave received by this listener will be longer than the actual wave. Now look at the difference again here. This is the actual wavelength. This is the wavelength as is received by this listener. And this is the wavelength as is received by this listener. Now look at the difference. The wavelength as is received by the listener in front of the ambulance is very small, whereas the wavelength of the wave that is received by the listener behind the ambulance is much longer. So here we have a source. Let's talk about the source moving towards a stationary listener. That means we are now going to concentrate on the ambulance moving towards this listener. Source moving towards a stationary listener. Let the velocity of the sound be v, and the velocity of the source be v sub s. So the velocity of the ambulance is v sub s, and of course the velocity of the sound is v. If the source is not moving, that is the situation on the left, the waves produced by the source will be spread out in a circle of radius v. Do you understand that? V is the speed of sound, means in 1 second the waves will travel a distance v. Now, suppose the frequency, let me give you an example. Suppose the frequency is 10 Hertz. What does it mean? What do you understand when you hear that the frequency is 10 Hertz? Well, if the frequency is 10 Hertz, it means 10 waves are produced in 1 second. That's the meaning the frequency is 10 Hertz. 10 vibrations per second. Each vibration will produce a full wave. So there are 10 waves produced per second. So the actual frequency is 10 Hertz.